Greetings, students. So this video here is the first of a series of videos that are designed to help you begin to review for the final exam. So let's get right at Unit 1 here. Unit 1 is about measurement systems and principles that relate to measurements. So our first set of ideas here, items 1 through 4, relates to something called the metric system. Now, the metric system uses a set of prefixes and base units to describe amounts. And for example, we take the prefix called milli and we place it in front of the base unit called gram. It changes the value of gram. We could do the same thing with that prefix micro, place it in front of gram. It also changes the value. The beauty of the metric system is that when it changes the value, it changes in factors of 10, which allow us to slide the decimal either left or right to make conversions rather quickly. Okay, so let's take a look at our first example here. It asks us to compare a centimeter and tell us how many times larger that would be than this symbol right here, which represents micrometer. So number one, centimeter compared to micrometer. So if we come over here, we will notice centimeter is positioned right here on the staircase, micro down here. So centi being above micro is a larger kind of unit, and we can count 1, 2, 3, 4 positions away, which means a factor of 10 to the 4th, which is why you'll see on the answer key here, 10 to the 4th power, which could also be written as 1 followed by 4 zeros. Let's take a look at the second example, comparing milligram to nanogram. So milligram compared to nanogram, let's locate them. Milli right here, 10 to the minus 3. Nano didn't make its way on the staircase because nano is a rather small unit. So we can see we are comparing milli at a minus 3 power and nano at a minus 9 power. They would be 6 factors of 10 apart, therefore, or 6 positions apart. So we say it is 10 to the 6 or 1 followed by 6 zeros. So a milligram is 1,000,000 times larger than a nanogram. So our metric staircase is a really nice way to make these comparisons. Okay, so let's take a look at an actual conversion where we're taking a unit called liter and we want to turn it into a unit represented by milliliter. So we can use our metric staircase once again by locating the units. So we'll go to the staircase and we'll locate liter. Let's clean this up a little here. So we see liter as a base unit, and we're relating that to milliliter. And what we do notice is when we compare them, they are 1, 2, 3 positions away. So what we're actually converting here is from the larger unit called liter to the smaller unit called milliliter. So since we're starting with a larger unit called liter and making a smaller unit, in order for the amounts to be equivalent, what needs to happen is the numerical amount must get larger because we're making a smaller unit of measure called milli. So the numerical value gets larger. It would get 1, 2, 3 positions to the right larger. So the decimal being after the 5, we have to add 3 zeros so we can move that decimal and then replace it right here at 25,000. Let's try our next example. A picogram, which essentially means 1 picogram, is equivalent to how many nanograms? So pico compared to nano. Well, let's take a look at that. Pico we see is 10 to the minus 12. Nano we see is 10 to the minus 9. So we see a distance of 3 factors of 10 apart. That means we need to move the decimal position 3 places. Well, in this case, we are making a larger unit of measure. Nano is a larger unit. Therefore, the numerical value needs to get smaller, and we'll have to move it 1, 2, 3 positions to the left. So the 1, and we would need 2 zeros to the left of it. So we could move it 1, 2, 3 positions, and 0.001 is our answer. Moving onward, what we're looking at, you're going to see that for many of you, you may have sort of forgot about this principle. The principle relates to the precision or the sensitivity of a measurement. So when we record a measurement, we're supposed to be communicating how exact that measurement is. And there's a strategy for doing that. Let's take a peek in our notes as to how we communicated that when we were in class. So here we are. We're looking at something called the precision of a device. The precision of a device or a tool relates to a decimal place. So basically what that means is, what is the smallest amount that it could measure? Like this ruler here, every little position, every time we advance one little space, we call that tenths. So this device has precision of tenths. When we look at this device over here to the left, this cylinder that's being read, we see that every time we advance one little space, we move up 1 milliliter. So the precision of this device is ones. The actual rule that we're supposed to be using tells us that we have to estimate 1 decimal position to the right of the actual precision or the sensitivity. So for tenths, the position to the right would be hundredths. With this ruler, it must have a hundredths position. Even if it's a 0, it must be included. With this particular device, since the sensitivity is ones, we have to estimate the tenths, even if it's a 0. So let's go back and apply that to the examples that we see now. We see when we advance this, if we were looking at the sensitivity of this, every little space represents an amount of 1 milliliter. So this is marked, not 1 milliliter. Every space represents tenths, Mr. Brewer. So every time we move one space, it's 1/10, 1/10, 1/10. For example, 52.1, 52.2, 52.3. Since it's marked by tenths, or the sensitivity is tenths, we have to estimate a hundredths place. Therefore, if we believe it's exactly on 53, it's not good enough to say 53.0. We have to add an additional 0 to communicate how exact this measurement is. And if we look at the device to the right of it, it looks like we kind of have the same thing going on. We have a sensitivity of tenths again, 6.1, 6.2, 6.3, 6.4, 6.5. So every time we advance one space, right, we are revealing a tenth. So since it is marked in tenths, we must estimate the hundredths. I believed it was kind of right on the 6.8 mark. So I estimated my hundredths to be a 0. If you estimated it to be 6.81, that wouldn't be wrong. You're making an estimate of the last position, and estimates are not exact, but they need to be included because we include, or we communicate, how exact a measurement or a tool is. Well, if we look at a ruler, once again, this ruler is also marked by tenths. Since it's marked by tenths, we must include a hundredths. So I chose to say it was 3.25, somewhere between 3.2 and 3.3 was the length of this bolt. So we don't know exactly where, but I chose to say it was about halfway between the 2/10 and the 3/10 mark. So if you chose 3.23, that would be correct. 3.2 with no other additional decimal location, that can't be accepted. And that relates to this next idea called significant figures. To examine a number of significant figures in measurements, really what we're doing is we're writing down measurements and communicating how exact they are. So it's not just counting how many digits they are, it's counting how meaningful the digits are. And all of the confusion comes in relationship to how we understand zeros when they're written down. So let's find our set of rules that we worked with in class that related to significant figures. And here they are. Our rules in green are our zeros that we count as significant. And our rules in red are our zeros that we say, yeah, they're not really significant to the measurement. So let's go back and take a look at the examples that we are working with here. So 25.00, these two zeros to the right of that decimal when we try to define what they are, I like to call those East Coast zeros. They're to the right of a non-zero digit, and they're to the right of the decimal. So there could be a whole string of them on the end, just like we see here, 1.0000. All of those are called East Coast zeros. We communicate those as being significant to the measurement. So this has two East Coast zeros. Of course, non-zero digits are always significant to the measurement. So the 2, the 5, and both of the zeros are significant. Let's take a look at number 2. In number 2, the rule that is the most important is this rule right here about leading zeros. Leading zeros could be a whole string of zeros before we actually get a non-zero digit. They lead the value. So this guy here is only 2 significant figures. Only the 1 and the 5 are significant. And we call those leading zeros. And that's exactly what we have going on here with 0.00012. They lead the value. So only the 1 and the 2 are significant figures. Moving onward, we see 123,000. The core idea here is there is no decimal position located in this particular value. So what we go back to look for is this particular rule right here about trailing zeros. When there's no decimal located, these zeros at the end of the value, they're not East Coast zeros. Those zeros are what we call trailing zeros. They trail or they follow non-zero digits. But when there's no decimal located, we never assume them to be significant. So we're looking at the 1, the 2, and the 3 are significant, but none of these zeros are. They trail the value, and there's no decimal located, so they're not really considered East Coast zeros. 3 significant figures. If we look at number 11, we got a series of rules. In number 11, we got a leading zero, doesn't count. We got a 2, which counts as significant. We got a 0 between the 2 2s. Well, that's a special kind of zero called a sandwich zero. Look, it says sandwich zeros. They're significant. It's sandwiched between 2 non-zero digits. So that 0 counts as significant. The 2 counts as significant. And the last 2 zeros on the end all are significant. So we have 1, 2, 3, 4, 5. Those last 2 zeros on the end are what I like to call East Coast zeros because there's a decimal and they are at the end of the value. It's kind of like they're on the East Coast of all the other information. Okay, so that's our review of significant figures. Let's move forward. And the reason we learn those rules is there are actually some true methods for understanding how to round. And one of those methods relates to an idea when we multiply or divide. If we go back to our notes say that the results from calculations should not be more exact than the measurements they came from. So we have 2 rules. When we multiply or divide, we round our answer to the least number of significant figures that the measurements indicate. So here, 1.50 is 3 significant figures. 2.7 is 2. The least number of significant figures is 2. So we did the calculator math. We multiplied, we got 4.05. And we said that 0 was the second significant figure. So that's where we're going to round. We looked past there, we saw a 5, we rounded the 0 up to 1. We report with 2 significant figures, 4.1. If we look at number 10, now we're not multiplying or dividing, now we're adding. Now there's a different rule. When we add or subtract, we round the answer to the placeholder or the decimal position that is less sensitive or less exact. Well, how do we know that? Well, look, I've marked them. 12.00 is exact down to hundredths. 1.3 is down to tenths. And 10.550 exact to the thousandths. Tenths is less exact than any of those measurements. So we do the calculator math. We get 23.85, but we round the tenths position, this 8, because tenths are the least exact decimal location in the data. So I look past the 8, I see a 5, I round it up to 9. Moving on to number 11. Now we're back to multiplying or dividing again. So we round to the least number of significant figures. 4 significant figures in this value, 3 in this. Do the division in the calculator. We're only going to be allowed to keep 3 significant figures. So what we're going to do is we're going to look at that 9. We're going to look past it. There's a 5. The 9 turns to a 0. When the 9 turns to a 0, the 3 also turns to 4. And we have to write 3 significant figures. So we reflect it as 4.40. Back to number 12. And now we're subtracting. Right now we don't pay attention to significant figures. Now we pay attention to decimal location. This guy here, 15.2, is exact down to the tenths. 2.61, that's exact down to the hundredths. Well, tenths are less exact than hundredths. So we're only going to be allowed to retain a tenths position with our answer. The 5 is the tenths place. Look past the 5, there's a 6. Let's round that up to 6. Call it 12.6, round it off to the tenths position. Moving forward, there's a concept that relates to reliable data. Reliable data has 2 conditions. It's both precise and accurate. So our question here is asking us, which of these targets simulates data that might be precise, but not very accurate? And precise really just means how tightly grouped. We sometimes, when we're looking at numbers, we look at the range, how close together they are. So A is very tightly grouped, close together. However, it's not really correct because we're assuming we're shooting for the bullseye. Therefore, it makes it not accurate. So you can have information that's precise, tightly grouped together, or a close range in values, but not close to what you were shooting for, the actual amount. Let's apply that to some actual data now. So here we are, we're looking at data. It asks us, which lab had the most precise measurements, and briefly explain why. Well, when we look at Harvard labs, the range of values ranges from 14.6, the lowest, to 14.8, the highest. The range is only 0.2 micrograms. That is the best or the smallest range in values, making the measurements very closely grouped. So we say that these are very precise. However, if we look at question B, who had the most accurate measurements? Well, accurate's more about who was closest to the real amount. The real amount is typically called the accepted value or the true amount. So it says here the known amount, right? Well, because ReliaCorp has multiple examples close to 12.9, 13.1, 13.0, 11.2. ReliaCorp lab is significantly more accurate, not quite as precise as Harvard labs, but it's closer to the accepted value, making it more accurate. And one way we can reflect how accurate data is to calculate this thing called percentage of error. The smaller that percentage, the more accurate the data is. So this asks us to calculate for ABC Labs trial 2, or number 2, what would be the percentage of error. So let's go to ReliaCorp's and look at trial number 2. ReliaCorp's trial number 2 is a value of 13. So it looks like we're going to pause the video here and make a real quick correction. My apologies, we highlighted the wrong data. So let's get with it, Mr. Brewer. We want to highlight ABC Labs trial 2, 14.2. So the math we have set up is correct. We take the measured value, 14.2, compare it to the accepted value, right? The known amount, 12.9. By subtraction, measured minus accepted, 14.2 minus 12.9 gives us 1.3. We then divide that by the accepted value, which is 12.9. So 1.3 divided by 12.9, when we multiply by 100, turns out to be 10.1%. 10%, not the best accuracy in data, but that's why we have percentage. We can compare how accurate one measurement is to another by looking at the size of that value. The smaller that percentage is, the more accurate the data is. So I hope you found this useful for Unit 1. Continue to look out for information for each of our units of study, and I hope you found this useful. Have a great day, everybody.